Today? Fun? Did it help to do that? Good. That's how it's supposed to work. All right, the next assignment, so you see I've got some assignments coming in next week, due next week, and what I've done is I've taken one thing that used to be one assignment and chopped it up into smaller pieces so that we can, there we go, that's what I was looking for. And so that's the situation. What we're going to do, though, is I'm in that assignment, you're going to have to use Minitab. And we've done a little bit with it before, but I figured I'd do a quick demo to get you on the right track with Minitab. So I figured this is the group or the example problem we did in class last time, where we calculated effects and all that kind of stuff. And so I would just say, how would we do this sort of thing in Minitab? So you start up Minitab, and I'm running this from the Citrix server at UND. So all the clunkiness of that is going to be here. So if you are a UND student, you can get in there and run Minitab off there. Anyone looked at that yet? Good. You get it to work? Great. OK, so this is what Minitab comes up, Minitab 16. I recommend first thing that you do is put the factorial design toolbar on. That's what I'm going to be using. We'll be doing response surface stuff. And some of the graph stuff is nice, but not necessary. So this is just menus that you can get into stat DOE factorial, but they're all right here in this toolbar. So the first thing that we do is say, if I give you this problem and said, we did these experiments, temperature, pressure, residence time, and we had 3 replicates, how do we analyze it? One thing that you could do is you could take this design and paste it into Minitab and then have Minitab recognize it. I think that's a little bit clunkier than just creating the design straight from Minitab. So when we do that, we want to create this design, right? Those are the experiments. So I want to create this particular design in Minitab. And what I showed you how to do this, -1, +1, alternating, that's called the standard order. And so if we create a design in Minitab using the standard order, then we'll be able to just cut and paste our results in there. So go to Minitab, create factorial design, 2-level, default, that's great. We have 3 factors. This gives us information that we'll use later when we do screening design stuff. So you just kind of keep clicking buttons and get things set the way you want. We want a full factorial. Again, a half fraction is what we'll learn later. And no center points. We haven't even talked about center points yet. 1 block. We haven't talked about doing any blocking on this. So we just have 1 block. And then we have 3 replicates at the corner points. And say, all right, we did the design factors. They're all numeric. They're coded the way we want them to be coded. So that's good. Options. Now here, when you're doing a design like this, we are going to randomize the run order when you actually do the experiment. You're going to do that. But we want to uncheck this so it makes it easier to get our data from Excel into here. Because if we click randomize runs, then it's going to come up all random, and we got to figure out where to paste our data. If we uncheck it like we did, it'll put it in standard order. It'll be easier to do. So that's a key piece in what we're doing here. Excuse me. And results. Defaults are fine for where we're at now. So we say OK, and it generates the design. So it just gives us the design table, right? So you see everything's in 1 block. We can ignore the center point. Run order is sort of meaningless. It's the same as the standard order. So up here, it's telling us this is what you told me to do. It gives you kind of a running report of the things that you've done and results. And then here is the worksheet, just like the Excel. And so notice one thing. I had 3 replicates, and it just put them 24 runs all the way down. And if you notice, the first 8 runs, I'll just do it this way. What I've highlighted, that is 1 replicate of a full factorial design, right? So -1, +1. So this is standard order. This is 1 data set. And so then runs 9 through 16, would be the next replicate. Right there. That's the next replicate, and then the last 8 are the final replicate. So what we want to do is we want to input our y, which is yield in this case. And so now that we know, so the key here is to match up this 61.4 with the correct settings here. And I just verified, hey, that's in standard order, so we can do this. We can copy this whole block here and paste it into Minitab. The Control-C, Control-V works as you'd expect it to. Then the second replicate, we can drop into Minitab, and then the third. There we go. So there, now we have successfully created the design and got our data into it. Wasn't too painful. So now some other things, options light up as to what we can do. So we want to analyze the design. It asks, what's your response? And it's guessing. You probably want yield. So what you have to do, this is kind of tricky. If you don't have it clicked in this response box, you're sitting here and you're double clicking and it doesn't do much. Well, that time it did. But generally, you have to click this box and then double click over here and say, all right, yield, that's what my response is. And then we go through here, just working through each of these boxes. The terms. What terms do we want in our model? We want the 3 main effects, the 2-way interactions, and the 3-way interactions. So that's good. That's what we want. Sometimes you might not want all these, and you can move them over, but I want them all in there. So that's good. Covariates, we haven't done anything, and we won't do anything with that. Prediction is if you want to predict a optimum value and get a confidence interval there, we'll do that later, so not in this set. Graphs, what plots do we want to make? And these are pretty standard what we want. So effects plots, we can have a normal or a half normal plot if you want. A Pareto chart is nice. Half normal and normal will be much more useful for us when we get into screening designs. You can make them or not in this case. Residual plots, residuals are pretty important, as in really important. And we want all these plots. This 4-in-1 graph is nice. This is what I really want you to do in every problem because it's a nice small way of presenting residuals. Then we haven't talked about it now, but generally we put residuals versus each factor. So again, you don't have to do that for this assignment. I'm just showing you. Once we get to the full practice, we will be doing that. So those are the plots, the graphs that we want. There's another location that we need to make more plots for the assignment, but we're just working through this box right now. Results, all these things are okay. We can put them all in there. And there's nothing in storage and weights. Yeah, this just stores it in the spreadsheet, and we're not going to do any weighted regression. So we've done all the things that we need to do to tell Minitab to go analyze the results, and it just did, which is nice. So residual plots, we'll talk about that later. Should be just noise. There's the 4-in-1 plot. This is all nice stuff. This run order is meaningless because we have not told it which runs we did in which order, right? So this doesn't have any information for this experiment. If we had a real run order, we would be looking at this. So we'll talk about residuals later. Pareto chart, you've seen this before. This 2.12, that's your T star. And then these are the T values of the BC interaction, of the interactions, or excuse me, all the effects ranked high to low. Right? So it's just a visual, it's a nice visual that you can present to people. These things are doing something, these things aren't. So the results that we got that we're really interested in, though, are over here. The ANOVA table we'll talk about much later in the class. But here's the results that we're really interested in. So it gives you, here's each term, and here are the effects. Just like we did in the spreadsheet, hopefully they're the same. So the effect for t was 21.7, t 21.695, hooray, they're the same. Coefficients we'll talk about later in the class. These are the t-values, and here are the p-values associated with each hypothesis test, right? So we have a hypothesis test. The mean of this effect here for factor A, which is temperature, the mean is 0 versus it's not 0. The t statistic is almost 10, so the p-value is essentially 0. We reject the null hypothesis. So all the things that you learned apply. Learned in chapter 6 apply here. And so those are the results in Minitab that we're after. So these, and then we want to make some plots. So the plots that came out in that dialog box are fine, somewhat useful, but there are these factorial plots that are useful, and we're going to generally like to have all these. So a main effects plot, interaction plot, and a cube plot. The setup is you still got to go through here and say, here's the yield. I want all the factors involved in this. Options just as for a title. And then set up the interaction plot, same business, yield, all the terms, and cube plot, yield, and do all the terms. We want the data means, not the fitted means. Those are the data is the results we actually got versus our model predictions in our plots. So these are, there's a cube plot. We've seen that before, so I'm not going to explain that. Then the main effects plot. So as its name implies, this just shows you graphically what the effect is. Right? So factor A, when we increase A from its low value to its high value, the change in Y is here. Does everyone see that? B and C. So you can kind of visually say, hey, temperature seems to be doing something. We've proven it's statistically significant. B isn't. C kind of looks like it might be, but we've already done the statistical test. Then the interaction plots, we've made some of these, right, for the example. But Minitab's a little bit strange in how it presents it. It presents all the possible interaction plots. So remember in the example, let me paste this over where we can do something with it. Let's go in here. All right, so there's the interaction plot. So remember, an interaction plot, it's y, on the y-axis is our response yield, and on the x-axis is just one of the factors, x1, x2, or x3, and then the series are the other factors. So an x1, x2 interaction would have, say, x1 on this x-axis, and then x2 at the high value, x2 at the low value. Everyone oriented okay with that? All right. So how Minitab tries to do this efficiently is it does have, all right, this is your y value, right? So this is your response. And then it says, all right, so it gives you these things that says, this plot is the A-B interaction. This plot is the A-C interaction, and then this plot is the B-C interaction. Does everyone see how those things kind of line up with the A, B, C here? Okay, so then the x-axis here would be B minus 1 plus 1, so that's where that comes. And the x-axis here would be C minus 1 plus 1. And then here's the series. This is A equals minus 1, A equals plus 1. And here, this is B equals minus 1, B equals plus 1. But keep in mind, those are the y values. So everyone see how these interaction plots are the same interaction plots that we did before. It's just useful to kind of see this, see how Minitab does it. And remember, in these results, when the lines were parallel, they were insignificant. And remember, our results showed that this This one was insignificant. That one was insignificant. The only one that we said is real, based on our results of our hypothesis test, I should say, was this one. And so it's saying, well, the effect of C it really, really depends on what B is set at, right? In one case, it's decreasing. In the other case, it's increasing. Does everyone understand what that interaction plot means? So then I want to circle back and say something important. Well, everything I say is important, but this is extra important. Okay, so there was a significant interaction between what? B and C? Is that right? So what's really important is if you have a significant interaction between B and C, it says you can't fully explain what B is doing without talking about C, and the other way around. So, but these main effects are trying to do that. They are trying to explain what B is doing without even thinking about C. That's what this is doing. This is what is C doing without even thinking about what B is doing, right? So when you have a significant interaction, let me move this down here. When you have a significant interaction between two factors, don't try to talk about or explain the main effects plots. So because that BC interaction is significant, we're not going to think much about this because it's fairly misleading. Maybe misleading. It's certainly incomplete. Right? Does this tell the whole story of what C is doing? No, because C is doing a whole lot more than that, right? Same with B. This is the main effect of B, but there's a lot more to the story. Not just, well, on average, B doesn't do much. Well, B does a whole lot. It just depends on what C is set at. And in one case, it makes yield larger. In the other case, it makes yield smaller. So make sure to write that down. You still want to make them, but you don't want to interpret them. Okay. Does that make sense? Right. So when you have a significant reaction, B and C, I would not even present the main effects plots to someone in a report. So if I was going to write this up in a report, I would put the main effect plot for A, that means something, and then I would show the BC interaction plot. And again, even though Minitab gives it to you this way, if you're going to put this in a report, don't show these insignificant interactions. I thought that was killed, sorry. It was supposed to be. I got to check my settings. All right, does that make sense? This means something, the main effect plot for A. The interaction plot means something. Everything else is insignificant, so you wouldn't really present that to your reader unless there was something there you wanted to show for some reason, hey, this is insignificant. Right? So that's how you would do this on Minitab. Any questions on using Minitab for this? All right. It works pretty well, gets things done pretty quickly. Okay, so there's maybe a couple things. There's S, that would be our SP. And then these coefficients and the standard error of the coefficients, that's real close to SE, but not quite. But we're going to talk about that in a while, actually real soon. So let's move on. this is where we left off. We were talking about a different example. This was that voltage example, right? So just to finish this off, we had gotten up to about here, as I recall. And we found, okay, we calculated effects. We calculated the signal-to-noise ratio of those effects, which are the T's. And then we compared them to the hurdle value and said this was significant. Remember, when we're saying this is significant, what we're doing is very quickly that is a hypothesis test on X1. Is the X1 effect 0 or not? And that, since 3.72 is further out in the tails than negative 2.3, we say yes, X1 is doing something. And over here, we say the X1, X3 interaction is doing something. And then all these other effects, here and here, we say, even though they're not exactly 0, their difference from 0 can be explained by the noise in the experiment. Does that make sense? That, okay, this number isn't 0, but it's just noise. We're saying all the rest of them haven't proven themselves to be different from noise. So we're going to use that. We're going to actually, our goal is to build a model. And we're going to get to that later. But, so, how would we present this data? Well, we've got X1, X3. There's this interaction. So we better make an interaction plot between X1 and X3. And that's what it looks like. Something like this in units in sort of real engineering units. There's Y, which was the voltage that we recorded. And temperature, I believe, was X1. And this was X3 at its low value, X3 at its high value. And this corresponded to the low and high values of X1. Is everyone okay there? So it's important to be able to put these results into words. And you would say things like, the effect of X1 at the high value of X3, it doesn't seem to be doing a whole lot, right? It's almost flat. So the ambient temperature doesn't seem to impact the voltage when the circuit is allowed to warm up for a long time. If the circuit's not allowed to warm up for a long time, then the room temperature has a dramatic effect. So if the purpose of this experiment was to try to test this voltage testing procedure and say, how do we get the best, sort of most uniform, repeatable measurements, you'd probably want to set X3 at the high value here, right? Then the effect of room temperature isn't going to matter so much, and you're going to get that same measurement every time you test the circuit. Does that make sense? That's kind of how, if you remember, that's kind of how the experiment was set up, is how do we make this thing as repeatable as possible? And so instead of looking for the biggest effect, you're looking for how do I make the least effect? Yeah? Minitab will generate this, and it will look like, well, I'll find it in Minitab. It'll look like this. It'll generate all three, and then you'll pick the one that's significant. Pardon? No, you don't need to add the labels for the real units. This, for your homework, these results are fine. So that's just extra work. Know what they mean, right? But you don't have to go relabel it. Good question. All right, any other questions? All right, let's do this group problem then. So this is pretty similar to the homework you did. problem in a while. Group problem music in a while. That's my fault. Anybody have a question? You guys good? Got it, Chris? Can't see. Got these results. Get as far as you can. Is that a question, Bill? That's the total. It's the total number of experiments. 16. Sure guy. Nice to meet you. So 16 lines. So two replicates. And I looked at that this morning. So that each experiment will have 2 data points, so that's 2 degrees of freedom. We're going to have 1 to calculate the average. So we have 1 so that's so we have so we have that's how you go from 2 replicates So just think of how many both cases, we're not getting these estimates of points. We're looking at how many degrees of freedom in this example, yes. Yes, and if we had 4 replicates, we'd have 3 degrees of freedom in each case. So T star is how many degrees of freedom went into your estimate of the noise. So always look at how many went into SP, and that's how many T Let's talk about degrees of freedom because lots of people have questions on that. So first thing that we should do when we start this is say, oh, we have 16 runs. To not forget NF is 16. Okay, that's a separate thing. And now let's think of, okay, how many degrees of freedom went into SP? Well, it tells you it's 8, but when I saw that this morning, I really wished I would have not put that on the problem. Okay, so we should be able to figure out that we have 2 replicates. So for each experimental condition, right, for each row, we have 2 y values, right? So there we have 2 degrees of freedom. We burn up 1 to calculate an average. And then the other degree of freedom we use to calculate the noise, S squared. So we could say for each one of these, we could have an S squared, and you have 8 of those estimates. Is everyone okay with that? So we're going to have 2 numbers here. We can calculate their average, and we calculate the variance of 2 numbers. So that would have 1 degree of freedom. Our question is always, how many degrees of freedom went into our noise? How many degrees of freedom went into S squared? So is everyone okay with 1 degree of freedom went into whatever that number is at the top? And then this one's the same thing. We're going to have 1 degree of freedom went in on the next row. We have 1 degree of freedom went into that variance, which was from those 2 numbers that aren't there. They're not displayed, not given to you. And for each of those, we have 1 degree of freedom. When we pool them all together, remember, what do we do for SP squared? We take this guy, so S1 squared, times its degrees of freedom plus the next one, S2 squared, times its degrees of freedom, on and on and on until we get to our 8th estimate of variance, right? So we have 8 estimates of variance. That's right here. We pool them all together, weighting them by their degrees of freedom. In this case, they're all 1, so we add up those degrees of freedom, we get 8. I mean, we can put down here if I can count right. That's how we get SP squared. Is everyone okay with that? That's what you did in the homework, right? So keep in mind, in chapter 6, we just had 2 estimates of variance. We pooled them together using the same formula. We're just expanding that now when we have more than 2 estimates. We have 8 estimates. We're still weighting it versus the degrees of freedom. Question?
So say you had a situation where, like, the first 4 runs you only had 2 yields, and then the second 4 runs you had 3 yields. You had 1 plus 1 plus 1 equals 1 plus 2 plus 2 plus 2 plus 2.
Okay, say that again. You're saying if for the first 4 runs we had how many replicates?
2 replicates.
2 replicates?
3 replicates for the last.
Brought it down. Okay, so in that case, you'd have some trouble. Otherwise, there's some practical things that's not, it's called an unbalanced design. But what Derek is saying, and it's fine for this example, it's good if he's saying for these, if we had 2 replicates for those 4, we would have 1 degree of freedom for each of those, right? And he's saying if we had how many? 3? If we had 3 replicates here for each of these, then we would have, then our estimates of variance would have 2 degrees of freedom in there, right? So then we'd have, what, 12 total in that case. Does that make sense? We will get to the case where the degrees of freedom aren't going to be the same for each row, but we're not there yet. All right, and then when we calculate SP squared, going by Derek's example, notice these bottom 4 variances will be weighted more heavily, right? Because we're taking that variance times its degrees of freedom right here when we're weighting it. And that makes sense, right? We've got more data into that variance. It's probably a better estimate than one of these in the top. So that's why we do a weighted average of variance. So, and again, we're assuming that the variance, the noise, is the same at every experimental condition. That's why we can pool it together. And this time, well, it just gave it to you. It didn't give you SP squared, it gave you SP, which was 50. So we can talk more about it later, but is it a little bit clear how it would pool variance? Somewhat? Yeah, Thomas. No, you don't square the variance. But S squared is the variance. S is standard deviation. That's what you mean. Yeah, S is standard deviation, S squared is variance. Okay, so now this was something, you didn't have to go through that because SP was given to you, degrees of freedom were given to you. But now we want to test these effects. Which ones are significant, which ones are not significant. So we need to do this hypothesis test. And so what we've been doing in the homework is, okay, we have T of each effect is going to be the effect divided by the noise in that effect. We don't know that. We have to go get that. So SE was the difference between 2 means, so 2 times 50 over the square root of 16, right? NF was 16. It's really easy to make that mistake. So that's at 25. Hopefully it is. It is. So that's the noise in the effects. SP is the noise in the individual measurements. We got to be able to figure that out and keep those things separate. So I'm okay with that. All right, everyone ready for a shortcut now? Exciting. All right, that's why you come to class. You don't just read the book. Okay, so we can calculate these t-values. So this is on an exam. This is what we do in the homework, and it's probably the right way to do it on the homework. But on an exam, that takes time, right? So we can calculate the t-values and compare them to our t-star. But we can think of our t-star as being corresponding to some hurdle value of the effect. So we could get there, instead of a t-star, we could calculate an e-star. So we're just going back one step. Instead of a hurdle value based on t, we're rearranging this fairly simple equation, and we're getting a hurdle value based on the effect itself. And what's the benefit of that? Well, then you only have to calculate one thing rather than all 7 of those t's. If you don't like this, you don't have to do it. If you like it, it might save you some time. So either way, we need a t-star. T-star is going to have, it's a two-sided test. Alpha is 5%. If it's not stated, we're going to assume it. And then how many degrees of freedom for our t? It's always how much went into our noise. And we had 8 degrees of freedom went into our pooled variance. How many degrees of freedom went into the noise? That's the same as our t-star. And it is 2.306. All right. So then, again, you can calculate all these t's and compare them to 2.306, or you could just do this times 25, which is SE, and get 57.65. And then you could look, if that's our hurdle value for effects, any effect that's greater than this or less than negative that will be significant. So that is outside of that. That is as well. So is that and that. None of them make it. None of the other ones make it. Did you guys identify those things as significant? So this is just a quicker way to do it. Okay, so now we want to maximize y. And we want to know, what do we set these guys at? So let's start thinking about this. Let's start with x2. If we're trying to maximize y, where do we want to set x2 at? Low value or high value? High value. Plus 1, so the polyethylene content would be that. That was easy. Now, x1. If we look at the main effect of x1, that's arguing that we should set it at the high value, right? So let's just put that down for now. We recognize we've got this interaction. We're going to have to deal with it at some point. But now let's skip down to x3 and say, what are we going to set x3 at? The main effect says x3 should be at its what? High value or low value? Low value to maximize y. But the interaction term, what is that telling us? The interaction term, it's positive, which means when these numbers here are positive, they're bigger than when they are negative, right? How did this number get positive? It means that x1 and x3, when they were multiplied together, had the same sign. So what this is saying, since we have a positive 62 and we're trying to maximize y, it's saying x1 and x3 should have the same sign. Does everyone get that's what that interaction is telling us? Because when they're the same sign, we get that result, and those four were had larger y's than the other four. Okay, but that contradicts what we've got here, right? Sorry, I didn't put the x3. The x3 main effect said this should be at a -1. That's this guy. The interaction is telling us x3 and x1 should have the same side, so we've got a conflict there, right? Which one do you think wins? So which one wins between this and this would be, well, whichever one is has the larger absolute value. Right? So overall, we're going to do this in using a model that's going to be a little bit easier in the future. Actually, we're real close to now. But in this case, having x3, since that's bigger than that, the x3 is going to win. That was a little clunky to go through. And when you have a lot of interactions, it gets clunkier. So we need a better way to try to pick the maximum conditions than what we just did. And we can reason through this, and with enough time, we can get there. But there'll be a little bit better way to do this, a lot better way. And we'll learn that next time. But here's the important thing, not more of a Friday cliffhanger, but sort of a Friday closure, is you don't set the interaction. This is the equation on the exam. Well, I will get people telling me x3 at the low value and then put a +1 down here for this interaction. You don't set an interaction. The interaction values are whatever your factors are, right? These are the things that we set. We set the factors. The interactions come from those. So don't tell me set the interaction at this level. It doesn't make any sense. An interaction can be at that level, but you cannot set it at that level. All right, have a good weekend.